Excuse me. Okay. Okay. We took a break. We're almost actually where I was planning on stopping because, of course, Dr. Young is going to return on Tuesday, and he's going to finish up. And it's my understanding he got through the Compton effect last time.
Yes.
He did.
Okay. Kind of getting to it, but yeah.
Okay, maybe I'm just going to kind of summarize it. You can see he's going to be all of this stuff. It could be really difficult, but he's primarily going to be focused on concepts, and so he's going to finish up. And the things that he's going to be doing, he's going to use some examples, and he lays out these examples. These problems are very similar to the ones I have on this review here. They keep reappearing. So I don't think he's going to be doing anything really tricky or different than those. I don't want to review what he hasn't talked about. I'm having enough time just trying to talk here. It's a lot of this stuff is not easy. As far as the ideas, though, the idea of the Compton effect, this is really what turned the tide with most physicists. The idea, the photoelectric effect, that Einstein was using the idea that the light came in bundles or packets of energy, was really counter to what they were teaching in physics. And what we've been doing, look at that in a bit. But the idea that this incoming X-ray, he's going to bring in X-rays, is going to strike a crystal, and the X-rays are going to scatter off of it, but they're going to lose some of their energy, and so they're going to end up with a longer wavelength. And in a crystal, there's all kinds of electrons in there. We can have a collision with the electron, and it goes flying off. And what this is really a classical picture of a little bit like billiards on the scale of protons and electrons. What we're playing with here is, depending if you're thinking of an ordinary collision where it comes in and hits the electron, it could go off, scattered off at some angle. This scattered is going to be an X-ray or another photon. Again, it's going to lose some energy and give it to the electron. They were able to read out at varying angles, and this is kind of the readout, that intensity of that scattered X-ray. For doing this, they use the idea of that it's an elastic collision, so that the light interacting with this is acting very much like billiards. So it's coming in, it's going to strike the electron, flying off, and it's going to get deflected off itself. And we use the idea that it's an elastic collision, so energy is conserved. We've got, this is going to be the energy of the incoming X-ray. Outgoing X-ray has its energy, and the leftover energy is in the kinetic energy of the electron as it goes flying off. Now, in addition to that, momentum is conserved in both the X and the Y direction. And we've got the momentum of the individual particle and the scattered particle, its momentum. We have the cosine of theta because we're going to have both X and Y components. We also have the recoiling electron here having X components to that momentum. We do it in the Y direction. Well, originally it was coming in along the X-axis, so the Y component is 0, and we have the Y component of the momentum of the photon or the X-ray, and the Y component of the electron going off. Now, it takes about 3 pages of work. You got 3 equations, and you can reduce it to this equation as a kind of a classic one. Where you can figure out what the wavelength of the recoiling or I should say scattered photon or X-ray is, depending on, and it's got Planck's constant built in there, and then the angle that it's going to be observed at. Now you can be looking at a whole bunch of these from all different angles, and they could solve this. They could also detect the recoiling electron, how it goes flying off of there. You could imagine if this is billiards, this would come in and these things could go off at different angles depending on how precisely they struck. So obviously he's not going to have you derive this equation. I've only seen one time where he's made use of that, where he gave you the energy of the photon coming in at some angle and asked to find the kinetic energy and the angle that the electron's going to go off at. But he only did that one time and he just killed everybody. So, so I think he's kind of scrapped that. So I don't think he's going to do too much with this. All of this is kind of laying the groundwork. But this was a real turning point in thinking that light carried this energy, these packets of energy. Think of like little fists that are going to be coming in and hitting things. The energy. Let me jump to the. Just to show you the confusion here in the book. The book doesn't help either. The fine print that they use in here. Now, this one maybe looks familiar. We derived this one in relativity. It was one of your homework problems. Okay, so doing that, and then they kind of make in the fine print that they say, okay, where was that here? Well, let me just paraphrase it. The idea that for a photon has to have zero mass. I mean, it's traveling at the speed of light, and if it had any mass, we'd have some real problems here. So the idea of the rest mass of a photon is going to be zero, so they just set that term equal to zero, and then they can solve for the energy is equal to the P, the momentum times, here's what I want to say first here, is the photon, that bundle of energy, would have this energy. This is Planck's relationship, or I should say Einstein's relationship for the energy of the photon. The mass is zero, and so E is equal to PC over that just taking the square root of what's left over. This is the energy of the photon. And also the energy, as Einstein's saying, is also equal to HF. So we can set these two things equal, end up with the momentum is got to be HF over C, and C is the velocity, which is the frequency times the wavelength. Frequencies go out, we end up with H lambda. This is what I was using on the previous slide. The book just sort of glosses this and says, oh, obviously the momentum is H over lambda. Got this relationship. Not helpful. And again, they just kind of mention this idea of this conversion from electron volts to joules. So take a look at this, and it has a lot of things that you really need to do all these problems, but it's just sort of sliding it in there on the side. Let's go back to Compton, and we're using the idea that for momentum is Planck's constant over the wavelength. That's a given there. In terms of energy, it's HF, but that's equal to C over lambda. That would be the frequency. So that energy of that photon is HF. Let me jump another slide here. Basically, the energy of the photon is HF. The wavelength would be H over the momentum. So, okay, so obviously these are subtle things in there, but they're really at the guts of this and important. Dr. Young will come back, I believe, and come starting on de Broglie waves, really sometimes called matter waves. But let's step back and see what a radical notion this is. The idea that the energy of a photon is this Planck's constant, which is really tiny little number, times the frequency, gives you the energy in a single photon. The higher the frequency, the bigger that chunk of energy, the bigger the punch of that, and so all these photons are of different energies and different frequencies, but this would govern what kind of energy or what kind of power was packed into the punch of one of these photons. Now, you recall that, think back to optics. We used the double slit as this classical experiment that got rid of this notion, at least they thought at the time, of particles of light. It didn't make sense as far as going through two slits, that there could be this idea of interference, and but this says electrons. Imagine this is photons here first. If we do the same experiment with photons, we can shoot photons, and we can, if you shoot enough of them, they start to pile up like this, and make a pattern that looks like this. But you can slow it down, so you can literally setting through these slits one photon at a time, and then on the screen they will start to fill in, and they will fill in just where there's these bright maxima. Anywhere where there's minimum, they won't show up there, so they only show up at these maxima. Well, this is a very wave-like property, but yet these photons, as they arrive, and they arrive discreetly, we can pick them up. You can have a photodetector like a CCD, like you have in a camera. You put them in. You start to collect dots, and they start to seem just sort of random at first. And over time, they develop into this classical two-slit interference. Now, what de Broglie is going to do, a real radical, he was a history major, and he's got hearing about these ideas. He ended up changing his major. He ended up getting his doctorate and a Nobel Prize from his doctoral thesis. So mostly, nobody else, I think, has done that. But his insight, and he got his ideas together and sent them to Einstein. It was Einstein that really said, whoa, we got something here. Again, he's making use of the fact that the energy is Planck's constant times the frequency, and the wavelength is Planck's constant over p, the momentum of the particle. Right now we're talking about photons. These are light particles. But he said, wow, listen to this. We've got the idea of light, which we know has this wave-like property. We've now discovered that, principally through Compton, is the one that really sold them, that this light is coming with these punches. These are particle-like in their collisions. If light has these dual properties of wave-like and particle-like, what about matter? Matter we think of as ordinary particles, like electrons and protons. The idea, could they have wave-like properties? And he suggested he did. They did, and they followed through. And when they did experiments, and ultimately they did the double slit, they didn't do it first for technical reasons, they ended up, if you shoot electrons through multiple slits, they start to pile up, and they too create interference. So they're very similar to that of light. Now, they've done this with electrons. They've also, now they're doing it even with large protein molecules, buckyballs, any kind of matter that you can be able to fit through these slits, running them through, they start to pile up like this, showing that they have these wave-like properties. So this is a direct duality in nature, and it has big consequences as far as our understanding of the universe. Dr. Young is, I think, he hasn't talked about the Heisenberg uncertainty principle, right? Okay, so he's going to get back in there. How do you make a particle out of a wave? If it's got one wave, if a certain given wavelength, it could be anywhere. the idea, if you could somehow make a wave packet, and that's what he's playing with, the idea that you could have a wave, you could make a wave packet by adding a bunch of different frequencies together, or wavelengths together, so they interfere, all lining up with lambda. And then we could get this is a wave packet. However, it doesn't have a well-defined momentum, and so therefore it doesn't have a well-defined wavelength. Dr. Young will talk all about this. It's possible to make this smaller and have it more localized, but then you start to lose the idea of what its wavelength is and hence what its momentum is. And so Heisenberg's uncertainty principle is the uncertainty you have of where is it? It's somewhere in there to what its momentum is, and that's always going to be greater than or equal to more things. H bar, which is really Planck's constant over 2 pi. This is just a shortcut way of writing it. This is the uncertainty principle in terms of position and momentum. There's another corollary to that, that's the uncertainty in energy and the time at which it has that energy. So Dr. Young will take you through this, and I think I'm not going to talk about this. I had that as an example to kind of show the nature of uncertainty, but I think in terms of where we're at. Next Tuesday, what you want to look for, he's going to talk about the particle in the box. This is a kind of a crazy one-dimensional atom. The idea that you have a box, meaning that you have large impenetrable sides, and that you could imagine you put an electron in there and it could be banging around back and forth. And so it will have, depending on its momentum, will have different wavelengths. And there'll be certain wavelengths that are allowed and certain energies that are allowed. And he'll talk about that. And he'll do a problem. Since he's going to do this, he's only got this particular problem. And you'll see that I do have some other ones that he's asked relating to this, and they're pretty straightforward, and the results are all based on this. So this is more of a preview saying, hey, pay attention Tuesday morning. He's going to do a problem like this, and that very good chance could show up on the exam. There'll be another one that he's going to get into that he's going to, in fact, this is it. Again, I'm not going to do it now. I'll let him talk about it. But be looking for this, and you can look back at my notes here if you want after the class. And this is number 5. Okay, this one still basically the same thing, just starts it at a little different place, but essentially it's the same idea. So watch for the particle in the box, and then he's going to take you into a look at the Bohr model of the atom, or the Bohrian model of the atom. The idea that what Bohr had was that the electron is going around the proton very much in a planetary fashion, and all of that is pretty much classical, like classical gravitation. However, it will turn out that there was this one rule that he had to apply to it, that the angular momentum had to be proportional to Planck's constant. So that he gave various fixed orbits that this thing could take. Unlike an ordinary planet system, you could have something orbiting at virtually any radius. This is going to have very fixed radii that it can orbit with. He's not going to take you through all the detail. There's some more in the book that you can read as far as the derivation of this. But I expect that, in fact, all these constants get crunched down into a single number, where the energy of a photon, basically if you're going from one energy state to another energy state, you can give off energy in the form of a photon. What is leading up to is these ideas of spectral lines. We did this a couple weeks in the lab, weeks ago. What Bohr was able to do is describe mathematically what all these wavelengths for, and this is just hydrogen, would produce. There's some in the visible part of the spectrum. There's another series in the infrared, and then there's another series in the ultraviolet. all of these spectral lines, he could, with the equations and these n values, 1, 2, 3, just counting numbers, be able to explain the wavelengths of all those lines. You'll see this again. You're going to see this idea of an electron volt. He's going to use this equation. It's going to kind of simplify to this. Anything that he might ask you is going to be for this equation. And he'll use this to describe how you can create these lines. Is really a change in energy in the atom. Either it gives off energy or it can absorb energy. You can go either direction with these. Okay, a lot of stuff. He's going to hit it hard on Tuesday. But this is what you should be looking for. So anything that he might ask you will probably be either a particle in the box or this idea of the Bohr model or some trivial questions from the stuff that leads up to this. Okay, I think I'll leave it at that. So definitely be in class on Tuesday. And wow, good luck on Thursday. So I'm sure glad I don't have to do this. Yeah. Okay, best of luck to you. Yeah, not easy to talk about. Not easy to listen to.
See you Monday, guys.
Oh, excuse me.